Everyone, welcome to another episode of RoboPapers. Super glad today to have Chong Zhang. He is one of the authors of this paper called Attention-Based Map Encoding for Learning Generalized Locomotion. Yeah. So thank you so much for showing up, Chong. It's good to see you again. Maybe as a start, if you can share a little bit about yourself.
Yeah, so I'm currently a PhD student with ETH Center. So I have two advisors. One is Professor Michael Wooter, who is also the last author of this paper. And another one is Professor Martin Richard, who mostly works on like large models and safety things. So you can see that my future work will be on both robotics and large models. So I'm a fresh PhD here. And this work is actually like the bridge work between my master study and my PhD, because my master study is quite long. It's like 3 years. So I spend a lot of time doing something like a PhD student. This paper takes in total almost 2 years. And the idea was from like 2 years ago, I was doing some small project. It's about if we can use end-to-end reinforcement learning to do like locomotion, because at that time we already had very robust locomotion controllers on like rough terrains in the wild. But still, like if we have very sparse terrains, we are still using MPC or model-based planning and control. So you might know another paper. It's called deep tracking and control. So that paper came that time as a complementary thing to the reinforcement learning things. But still, it's like it uses a model-based planner to generate references, and then it uses reinforcement learning to track such references, such that the planner is very generalized to different terrains, and the tracking controller is very robust. There's a strong limitation here is that you have to first generate a reference by model-based planning, and this is not an easy thing because it requires a lot of tuning and for training, because like classic model-based planning happens with CPU. So you have to train IO with 4,000 environments with CPU. So this takes like 3 weeks also to train. Then you have to do it on the real robot. So you are with very limited computation on board, but you need to run both a model-based controller, model-based planner, and the IO controller. And you still need to run all perception things. And also because this is a model-based planner, so if the map is kind of noisy, or if some model has a mismatch, then this planner will fail, and then the whole thing will be off because you cannot check a bad plan from a wrong planner. So that was actually my first project in ETH. It was about checking if we can do sparse strings with just end-to-end IO, because like previously also has many trials, like we used neural networks to imitate outputs of MPC or similar things, so that we hope it can generalize or do something good on sparse strings, but it turns out it cannot. Yeah, so that came my first work is about just how to tune curriculum and the rewards and all kinds of these things to make the robot work or run on sparse terrains like stepping stones and balance beams. So it's actually iOS paper. But at that time, I just found that it cannot generalize, because in model-based planning, you can easily get a very generalized solution. But in IO, if you get some OOD data into the model, it will just output some random thing. So that was a pain at the time. But
Could you explain what you mean by tuning the curriculum a bit? I think maybe
yeah,
it's
so
useful.
as like actually your podcast has some paper sharing something, so it was a very old paper. So you can see the paper here. It's a very old paper, actually. So here you can see that for this kind of sparse strings, we first do some we start from a very easy and dense stepping stones, and then we go to a bit sparser ones, and then go to very sparse ones. But still we call this string stepping stones everywhere, because you can see a stone everywhere. And then if we want it to work with different sparse strings, we need to fine tune this policy. So from here, you can have a sense that it kind of learns some kind of behavior, but still this behavior cannot generalize. You need specific training for specific terrain. So actually this strategy was used by some recent papers, like there was one called it should be called Beam Dojo. So it was also in your products, so they are also using this curriculum. So I think this is kind of a magic solution to the sparse terrains. If you want to overfit one kind of sparse terrains, you first get such a stepping stone policy and then find a new terrain. But of course, like this solution is not good because you cannot randomize all of the possible terrains in the world, and many terrains are really, really weird that you cannot easily do something like procedure generation in simulation. Yeah. So from here, we have some confidence is that we can do something with end-to-end RL that is kind of comparable to model-based control, but still we need to improve the thing to make it really generalized.
And by comparable here, you mean comparable in the sense that it can generalize to previously unseen strange environments.
Yeah,
So like
it
this,
can
yeah,
work
yeah, okay.
on thin terrains.
So it can walk on very strange terrain. So if you can't make this out, I guess the one in the upper right is like a bunch of pegs, right? Like there's a bunch of like individual like 4x4s or something.
Yeah.
Like very thin pegs that the robot has to walk across to get across the field. Okay. Yeah, cool.
So actually, like when doing the hardware experiment, I met a very funny thing is that when I trained the like balance beam terrain, so if I do not randomize like gaps between the static platform and the beam, then because on the real robot you can see here between the platform and the beam there was a gap. So it will fail on this gap. It took me a lot of time to figure this out. So that's also motivation that we should do generalization instead of just brutally randomizing everything we can.
So how do you do generalization? So the core question is, how do you do generalization without
Yes.
just purely doing domain randomization? Okay, cool.
So I'm going to the paper page. Wait. So here you can see my slideshow with this paper, and I would like to use the photo here. Let's see. So generally, because all model-based things or model-free things, they kind of share the similar, let's say, architecture is that you need to process a map and then you get this kind of encoding to you do some control-based thing for this coding. For example, if you do model-based control, first you use the current states and your map reading to decide which are the future contact points. And then you have a like whole body controller to track these contact plans and maybe trajectories. So there's kind of hierarchy of first processing your perception information and then do dynamic thing. So this is a like very strong inspiration for us because we also think that the reason that model-based things can generalize is that it first selects which are the best candidates for footholds or for contacts because it decouples contact planning and control planning. So here what we are doing is actually the same, but we replace this like in the model-based control we use like heuristics, we use like roughness scores, we use all kinds of heuristic scores to score each point in the map to decide the foothold. But here we actually can replace it by an end-to-end neural network. So here there's a attention map that you can see that as the robot goes forward or goes sideways, and when I have a command, so it can actually select which points on the map should be the foothold. That means that if we can kind of squeeze this map, the whole big map, into some foothold candidates, then this is a much lower dimension of embedding, and that means it can easily generalize and can be kind of robust against all kinds of different terrains, because even when your inputs change a lot, as long as it's selecting the same points, then your latent embedding will not change a lot. It will stay in distribution, and this will make your controller work. Yeah. So this is the whole idea of why we want to do generalization and how roughly we want to achieve generalization inspired by how model-based controllers work. But the thing here is that how do we achieve such kind of selection of foothold? Actually, here a very ideal solution is just use attention, because we all know that if you have attention, it can just select some points. But here we actually want like a competitive attention. That means if you are selecting this point as your foothold, then you are not selecting the other one. Yeah. So here comes our neural network representation. So you can see that here on the bit left part, we have the map scans, and which is a perception, and we have the proprioception, like joint space things. So with this perception, we just use some CNN to extract some local features. So each point has its neighborhood information, and we also have a position encoding. But here, because we already have like 3D positions in the space for this map, so we don't need to do positional encoding like CV or NLP people do. We don't need like sign signals. We just use the 3D positions here, the coordinates, and we just concatenate these things and to get a like point-wise map feature, so that for each point there is a neighborhood representation, which is kind of similar to how we evaluate footholds candidates in model-based control. We just use roughness, but here we can use, actually it embeds more information, and then we do a multi-head attention. We use our command and joint observations as a query, and use this pointwise map feature as key and value. So this means that we have like, for example, 500 points, but based on our current proprioception and command, you can only select some of these and get an embedding from this. So here we use like 16 heads and 64 dimensions of multi-head attention, which is quite low, but happens to be enough for our task. So here we actually did some ablation. It's like we tried 8 head or 4 head, and they did not work. But after 16 head, it will always work. So that's kind of brings the intuition that such kind of locomotion might be a 16-dimensional task.
Interesting. Yeah.
So here we already have a attention-based scene that can get some points from the map based on the command and proprioception. And this embedding just directly goes into a following MLP, and it can generate action. So here it's just an end-to-end network, but it has 2 parts, and the first part can act like a planner. So it's like, sometimes we say that we have some structure prior. So this is like a structure prior. We enforce a network to do selection for footholds, but it's differentiable, and then we just put it into end-to-end hosting. Yeah, so this network can be trained with IO, and it's end-to-end.
Sorry, can you explain to me why the map scans are by 3? Because I thought, like, you're seeing these 2D images on the bottom. Why is it? I don't quite understand the dimensionality there.
Wait, let me find this. So here you can see that the map just means that assume you are the rubber is here, and you have some rays.
Okay. Yeah.
From the top of the rubber, you just cast this rays downwards. You hit the trims, so you get a grid map of like height of each point. And on the real robot, it's coming from like, usually it's from autometry and some mapping methods, like here on this quadrupedal, we were using a LiDAR-based LiDAR inertial kinematic fused autometry, but it's for the field, so I guess indoor you can use just VLO.
Yeah.
And And we have depth cameras like around the robot, so it can get this depth points to, it's a point cloud, and then it can be processed into a map.
Okay, so I guess that's that question. So it is really just a point cloud. It's a big fused point cloud of all the things that those depth cameras can see.
Yeah,
okay.
It's a fused thing.
Makes sense.
Yeah, but on the humanoid, because we don't have the space of the hardware for perception, then we had to use mocap for optometry. Yeah, but as
principally, like this is just taking raw sensor data in and predicting where the robot should step.
Actually, like on Unitree, it's a dual pipeline. Yeah.
Okay.
Here, our hardware was not so ready at that time. Yeah. So we go back to this scene, and so here you can see that because we are doing end-to-end reinforcement learning, these behaviors can just emerge by maximizing rewards. And you can see some features like, for example, here we want it to do like different trains and different commands. So you can see that on this beam terrain for the bottom row here, is turning command and beam terrain. You can see that even when we want it to turn, the attention tells that you should only walk forward. So it actually means that we are doing something like constraint thing. So we are actually achieving the constraint coupling between perception and action with this just the reward and this attention thing. So this is a quite nice picture and it makes our development much safer.
Interesting. So it's like in practice, let's say a human is controlling, let's say, make an error and say, I want to turn left, but clearly turning left means the robot will fall over. What you have here will, despite the almost like an impossible command, the attention will still be, okay, you should turn left. You can only go straight. Okay, that's
so
awesome.
That's a feature I really like. Yeah. So
yeah, and I know you actually have some videos. Do you want to show some of the videos like in practice? Because you guys do both quadrupeds and
so I'll play the main video here because here you can see an overview of our results. So our first video is about we achieved a single row of stepping stone with a humanoid. So I guess at that time or even now is the only one that can do this. And it's a generalized policy. So we train the quadruped and the humanoid with exactly the same pipeline. And you can see that quadruped can also traverse this kind of very tricky terrains in the wild, so which is mostly designed for search and rescue. Yeah, but it also means that it's doing arbitrary terrain rather than overfitting the training terrains. So actually, like for these videos, we collected all like 4 continuous success to show this stable. Yeah. And here is the visualization of what I mentioned just now.
So this again is just like these are scenes that it weren't all in the training data, so it can handle. Or very cool.
And here you can see that in simulation can just we can just visualize this attention scores. So this actually gives us the confidence to make this what a big one.
It's really cool how interpretable this is. How it really is just telling you this is where I'm going to put my foot next, right? And that,
yeah. And then we have just like you can see here. This is all of our training terrain. Just a bit very simple, straightforward. Yeah, and it already learns very good behaviors. So you can.
So these are all of them. So like you showed examples of it on like going up and down and like so it learns all of that stuff basically just from like these crazy examples. Like see here, that's not in your training data. Is that right? Yeah.
So you can see the figure here. The part A is about what we train the trainers, the robots on, and then we find that it can directly generalize to like the trains in part B here. So it's more randomized. and not seen, but still like we are already having the stream, so we think why don't we just find it on the streams and make it more safe to deploy, and then we find it again on these small tricky terrains. But even before finding it already has a very high success rate here. So you can see that on this kind of parkour terrains, like in the part C, both humanoid and the quadrupedal can traverse this kind of complex thing. Yeah.
I'm curious, Chong. So right now, the command input is, like
What does
turning
it?
or going forward, right? Those are all done at so-called constant speed, I assume for now. But
Yeah.
but I presume nothing stops you from, including the desired speed. Let's say I want to go forward really, really fast.
Yeah. Actually, it can check the speed. I will show it later.
Oh, okay, cool.
Yeah. So like we just train on these trains and it's already very good. And then we further added some tricky terrains and we added a lot of noise here. So this makes us more confident about real world deployment. But actually I don't think it's really necessary. So it's just a kind of confidence for us. And then I'll show like some image behaviors here. You can see that and these are just like repetitive success demos we collected. And by the way, here on the beam, we can see that even on a very unstable beam, it can try to stabilize itself. So on the top left, you can see the beam is just shaking, but it will stabilize itself. On quadrupedal, we also collected some demos. So at this stage, we already found that like terrains like stairs are too trivial for us. Yeah, so we want to always show this kind of demos, and it can do such things in the wild.
You got to be pretty confident to walk that robot over some of these.
Yeah.
Nice.
So for the stair, we just speed up by 5 times. Yeah, and then here you can see that because we are training with reinforced learning, you can see that even in such cases that you have a slippage or because your terrain is deformable, then your feet is stuck into the tree. If you are having a model-based planning, then because of you are having like context on the knee on this unexpected path, then your model-based planner will just fail here. But for our learning-based controller, it will just learn to use the knee to recover, which is quite trivial for a learning-based controller. Yeah, here's another demo showing that you can do balancing even on these unstable terrains. And also like here it slipped, but it can still recover. This is also a very important feature of iOS is that it's very robust and being able to recover.
This is because you're giving it lots of domain randomization, right? Like impulse forces, things like that.
Yes. Yeah, but here you can also see that when like the contact thing is not so good for it, it can do such hopping motions. You can hardly plan this motion with model-based.
It's a little bit
I
like
tried
Kung
it
Fu
by
already.
my own. Actually, personally, I cannot do it. Yeah, I almost fell on this turn. Yeah, so the thing.
Yeah, that's pretty impressive, honestly.
Yeah. So in model-based planner, it's also a concern because like usually you want like real-time deployment, you want real-time planning, then you usually predefine some kind of gate. But this actually limits the potential of the like whole system. So if you can free the gate, then you are more flexible and can be able to recover even in this case. Yeah, and again, this important. Yeah, okay. So this is
sorry,
kind
Chong, you were saying you had something about speed, right? Like
yeah. It
I'd love to see that.
Okay. Later. Yeah, here it's actually like we control the speed and the orientation together with the joystick. So you can see it's sometimes slower and sometimes faster. This is actually very hard to teleoperate. So actually, I think one important thing is that we need to make it autonomous navigate.
Sorry. So what's happening in there? What's happening there is you have a human that's teleoperating this quadruple, right?
Yeah.
And it's, I suppose, yeah, it's too difficult for the teleoperator to say slower or faster because it's all very terrain based, I suppose. So what you're saying is that the model is able to adjust the speed up kind of accordingly based on the
this speed is controlled by human.
Got it. Yeah, but what I'm saying is that like imagine if the the humans put a speed that actually, put you in the place where the attention say, okay, you cannot go there. Despite the input at the speed, it will still limit it, basically.
Yeah,
It will slow
so
it down.
there's kind of tricky thing that the teleoperator need to be experienced to know about this. So actually you cannot just find a random person to teleoperate the robot. So that's why in the next stage we foresee something like learning-based navigation to better use this kind of controller rather than we have a human commander.
What makes it so hard to teleoperate?
Yeah, because like you are not the robot, so and you are not observing the robot state space. So you don't have full information here, and you are not very certain about the robot's dynamics. You are not sure if you give it a like 1 meter per second command, how far will it go and what's the acceleration. You don't know. So you just
Got it.
roughly know it can go faster or slower.
Right. Okay. That makes sense. So, okay.
Yeah.
Yeah, but I think still this already is a huge improvement for teleoperation.
Yes,
I
of
mean,
course.
sometimes you do want the human to be in the driving seat, so to speak.
Yeah.
But the human is not going to do any of this like terrain thing. It needs to be handled by something like yours. So the better performance it is, the real-time controller. In fact, the easier it will be for human to just like use a gaming controller and do
Yeah.
this. Yeah, this is really cool.
Yeah.
Yeah.
And here is go ahead.
No, I just want to. This is maybe a bit of a tangent, but but I wanted to ask about. You've been comparing a lot to model-based methods. I would like to go over like why the attention map kind of in particularly enables this robustness, or what's so valuable about that in particular.
Wait. So, about, I think there are two stands
Yeah.
or two layers of robustness. One is about like for recovery or all kinds of IO-based things. So because we are training with end-to-end IO, then we are good at these things. And another sense is about the attention makes it more generalized and
Okay.
yeah. So this is like two things combined together, and that's the benefit of using NDIL.
As opposed to other architecture. So okay, that makes sense.
Yeah. And this demo is for like we change the speed on the fly. So it's first slow and then it goes fast. So you can see that it's doing acceleration even when balancing.
Oh, I see. So, but this change in speed
This is
is
impressive.
basically controlled by I mean, it's
Human.
a command given by either a human or like you guys, right? I see.
Yeah, it's we command it with the joystick.
Interesting.
Yeah. And here you can see that we first command to go like 1.5 meter per second, and then it will do you see that just one step for entering. But if we make it slower, it will do like 2 steps on entering.
Interesting.
Yeah. So this is really controllable.
But I
Very
suppose
cool, yeah.
if you don't give it command, it might just
Stand.
just stand, right? And then
Yeah.
I see. Okay, interesting.
Yeah. So actually for us, you need to learn like which commands are the best for the robot to traverse this terrain. Of course, it can have some robustness, resilience, but like if you do one step per terrain or if you do 2 steps per stone, it can still be a different effect. Yeah, but this is like a visualization of attention simulation. So you can see that it's purely randomized terrain and it can do all kinds of gate switches and the tension is always correct. Yeah. So
how much of a difference does the map resolution here make? Because it's
here we
interesting.
have
It does
some
look like it's so good.
the pre-simple size. This resolution should be able to capture the minimal like gap or like the gap here because it should be able to represent the gap or the stone.
Yeah.
So because the stone is roughly like 20 centimeters, so we have like 8 or 10. Actually, it's 10 for humanoid and 8 for quadruped. Because like humanoid kinda has a bigger.
Yeah.
And so for quadruped, the map is also much larger. Because the size is big, so it has to see much larger map than a humanoid. So that leads to a very high dimension. Like when training multi-head attention, if your like if your length of key is too high, then it's very memory consuming. So actually, like due to computation constraints, we are like trying to have as large resolution as possible, but still be able to capture these the most fine-grained turn details. So
Yeah.
that's a balance here. Yes.
Yeah, I'm curious that how big is this model you end up like actually deploying? Is it actually a very small model in the end?
Yeah. I mean, it's small compared to large models,
Of course, yeah. Like,
but
is it
actually,
something you
like
can? Mhm.
we run it on CPU on NUC
Mm,
with oncs runtime. So the inference time is just like 1 millisecond.
1 millisecond. Oh, I was gonna ask that. Okay, so 1 millisecond. Okay,
Yeah.
and then but so actually then you're how about the lidar and all that? Like what are those like? What is the bottleneck when you actually do it in this actual physical robot? Is it more just a lidar? Mhm.
So first, you cannot have drifts. Because if you drift, you can easily misplace the foot. And so it's important to have a good LiDAR or a good odometry,
Mhm.
especially for quadruped. And the second thing is that actually I will complain here about like real sense cameras because they are so fragile in the wild.
Mhm.
Yeah.
So we actually need to do some filtering, like we may decide some feature to get it more get the map more clean and make it less noisy. Because real sense really has a lot of artifacts and the floating point in the air. Yeah.
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 So I think it's a lot of engineering issues about perception and mapping, but I feel these things can be solved easily with better hardwares.
Better cameras. Do you think you
Yeah.
could do like learn depth or anything, or do you think that would add too much latency? Because I feel like the multi-view reconstruction something.
Actually, I'm not sure because like in our pipeline, mapping is also running very fast at like 50 Hz.
Not fair. Yeah. Okay.
It's not a
So,
burden here.
but
Yeah,
you're kind of compute constrained, right? If you're running it on just a
yeah.
CPU, like you can run it on like a Jetson or something without, I don't know.
So we used the one just already. That's enough for the whole mapping.
Okay.
Yeah, but yeah, the engineering is a bit painful here. Let's see.
Yeah.
Yeah, yeah, and actually, like a hidden issue here, not in this paper, but might be in some new papers, is that like there's occlusion things. So if you have a very heavy occlusion, which can happen if your morphology, if your body shape, or if your sensor configuration is not so good, then it will have like occlusion issues. Then in that case, you might need some uncertainty based things for filtering the mapping, or maybe you need to redesign your sensor configuration. So I think here there's still a lot of like engineering details to be done correctly to make this work. Yeah. Yeah, and I think I can show here we also like compare to like previous like DT deep tracking control and the so-called naive anti-NIL. So you can see that in this figures part A, the second figure, we visualize like the success rate and video result stack rate of all kinds of trains. We see that even the deep tracking control can do only like 60 or 70 success rate, but we can do almost 95 also. So this is largely because like on the right, we visualize like the success rates for different trains. So you can see that the DTC, which means you use a model-based planner, then use R-based tracker. So on this plot, you see that there are some trains that this DTC things can struggle. This is because the planner will just struggle with these trains because it has a predefined gate and needs some like heuristic cost for planning. So you can see
So
that big. So because we are training with IO and end-to-end for everything, then it just like throws away the limitation of this model-based planning thing. So this is also another motivation that we want to throw away the model-based planning.
I see that. So palettes. It seems that palettes is one of the lower success rate, along with I think gridstone small. What is palette again?
Palette is like multiple parallel beams, but
Oh,
it's not.
okay.
Yeah,
Like a wood pallet, yeah.
Why do you
Is the
think it's
problem there that
struggle?
the foot gets stuck?
yeah. So for palettes, actually, we made the leads very small. So for model-based planning, usually it has some like you need to optimize like a collision-free trajectory and with some footholds. So it needs to center the foothold in the middle of like a beam. And then sometimes the geometry is not so friendly for such kind of planning things. You cannot easily optimize, or you just get into local minima for a so-called collision-free kinematic trajectory. Yeah. And for grid stones, and especially the small grid stones, this like the case because like when the stones are small, then sometimes the planner can hardly identify it as a terrain because like model-based planners are very sensitive to noise. So in planners, we usually like post feature the elevation mapping so that it can present clean areas of terrains. But if you have just small stepping stones, then it's hard for this kind of filtering to work, and it's always like manually tuned things, so it can hardly work on all kinds of terrains. Yeah, but with this achievement, you just train it and do it.
And how about some of this ablation study you did on the two-stage training and the network structure?
Yeah, so basically we found that if you directly train with like noises and heart rates, actually it can kind of work, but definitely it will take longer because like typical convergence of RL is that you train exponentially long and then you get linear better results. So if you just do like same iterations, then the convergence is much slower. So that's natural because if you first train with previous information, then it will converge faster. So it will save your GPU hours. Yeah. And also you can look at like the part C here. So the left part shows like a learning curve. So in our reinforcement learning setup, it's like there's a crack one. So if you conquer an easy terrain level, it will go to a harder level. But if you can finish the hardest level, then it will go to random level. So this design enforces that you first start from easy things, but when you can overcome the hardest things, you are still able to conquer all of the different terrain levels. So ideally, convergence curve is like your terrain level goes up, and after you are able to finish the hardest one, it goes down until some like stable point. So here the stable point should be 6, and the purple curve here is ours, and we also evaluate against like naive transformer encoder and also VIT things, or we just like we have CNNs, but this CNN. So in our attention-based pipeline, our CNN, we want to extract point-wise features. So we just do like always we always pad the CNN so that it's keep the same shape as the input. Yeah, but here we also try to downsample so that we can reduce the token number to 1/4 of. So the training could be easier, but turns out that it cannot learn very effectively. So this is interesting because I think that we are using like the maximal resolution that can capture the details so that if we do downsampling, then it might lose some information here. Yeah, but like our operation against like VIT things also show that you cannot just borrow some architecture from other domains like civil NLP to expect it to work. Also, that this transforming code actually like we did something like we put proprioception into a token and we put like vision parts into some vision tokens. So it's exactly what is happening with like vision language models. You just tokenize everything and put them together, and we find that the learning with this architecture is harder and it doesn't show any kind of generalization. So on the right, you see there's a lot of success rates on different trains, and the gray parts are for the trains that are not seen during training. So you can see that only our pipeline can generalize to these unseen ones, but for all these base types, they are not working. Yeah, I assume that our structured prior actually helps a lot here.
And you think a lot of this comes from that simple separation of like one part of the model is essentially choosing where to put the foot, and the other part is doing the control. That structure is what you're referring to here.
Yeah, we actually looked through a lot of paper to find these pipelines.
Yeah, no, it's very cool that kind of sort of very meaningful distinction works so well. Like, and it's
Yeah.
I really wonder if something similar could work for manipulation, like whole body manipulation or otherwise. Just like there have actually been similar works in manipulation, but never fully end to end, I think.
I think there are some things for selection here. So here you see that we only used like 2.5D map. We are not 3D map because that for 3D, I think if we want to achieve such advancing things, we need to do something like tokenize every voxel. This can be very expensive for our GPUs.
Yeah.
So
there's stuff like bin picking or there's a lot of manipulation stuff that is still 2.5D, I would say. But that's fair. Yeah. That's so you think it wouldn't quite scale as well to like real manipulation. That makes sense.
It can be hard. And also another point is that my idea for manipulation is that you better use something like a BPS, like a basis point set. Because that thing actually is similar to the mapping here. You just like have a mapping around the object. So I assume if we apply these things to like basis point sets representations like this, it will have a kind of similar results with attention. Yeah, but still it could be issue because I think BPS is not for deployment. It's just a concept in simulation.
Yeah. Chong, do you have more from the paper you want to like show? Because I actually want to run by you some of the things that you put out on your tweet. I thought those were actually quite interesting.
Yeah. Okay, let's go to the Twitter time.
You go to the tweet?
Yeah.
Okay. Yeah, because I thought you.
Yeah,
you said a few things that was quite interesting. Like, so I'm just going to run by you, one of these. Okay, so the first one you say here, quadruped versus humanoid. You said in terms of locomotion, there's no difference. Both can be learned well through end-to-end RL and similar training pipelines. I think, your paper kind of shown that. You did say something about humanoids until humanoid get strong arms and correct senses. What do you mean?
Yes, because like currently you can see that for locomotion, we are not using the arms. So this is actually constraining the robots. For example, that if you fall onto the ground, you need the arms to recover. But maybe like if you climb very challenging terrains, you're also using your arms, and even on stairs, you're using your arm to aid yourself.
So you're not you are using the arms at least now to balance, right? Like it is.
Yeah, but we are not using arms to contact the environment, to do interaction. So
yeah, makes sense.
So the point is that if your arm can be as strong as humans' arms, then you're actually like a more powerful quadrupedal. You have 6 dots on each limb. You are still quadrupedalized, you are more powerful. So that means that if you can make a humanoid with really strong arms, then it could be better than quadrupedal with just 3 dots on each leg.
But for that, but when you say be getting close to the,
sorry,
go ahead.
But I mean, you say correct sensors. Like, what kind of sensors are you thinking about?
I mean, it's just about first, maybe about contact, but I'm not sure because there's a lot of occlusion things. So as I said, if you cannot get the good sense and layout, then you have a lot of struggling on perception part. But maybe you can infer things from context. So I guess in the future there could be something about sensor fusion because it's not so easy to get an ideal sensor layout just like when you're doing bipedal locomotion. There are so many questions.
I was going to follow up on the humanoid point because I think it's interesting. But like having that in that case, it sounds like you would want to like you would need to solve that 3D problem that we were talking about with manipulation.
3D,
so handling a much larger
goal.
Yeah. Okay.
Cool. Number 2. You said here imitation learning or learning from demo for locomotion, right? And you said there might be a point for specific applications and markets, but not so useful if you can learn the skills correctly without those guidance.
Yeah.
Could you comment a little bit?
It's a hot
Yeah,
take.
so basically you can see here is that the condition is that if you can learn the skills. So basically when we do learning from demonstration, it's about two things. One thing is about to make it more stylistic, it's more beautiful, natural, but maybe not so optimal. And the second thing is to guide the learning. I mean, it's totally okay to guide the learning if you cannot just learn the skill without any demonstration. But if you are already able to learn the skill, just want to make it more natural, then this actually do not bring more optimality to the controller. And also it actually might constrain the controller because like, for example, in our demo, you can see that the robot can take different gates to traverse the train, but if you use the specific reference, then it will just be able to do one kind of gate. So this is kind of constrained.
Got it. So you're saying imitation learning actually more it's maybe for styling, like, you know, maybe people want to see the way people move like more like a dancer, but maybe the
Yeah, but still
dance,
like
yeah.
if you are not able to learn something directly, you need a demonstration.
Yeah. The next one, you say, you know, what is generalization? Why attention? You say, imagine a 400D grid map. Every grid can be steppable area or not. This is already 2 to the power 400 possibilities, even before considering different heights. So to work all kinds of terrain, many unseen during training, attention plays a role. So I guess that's basically the key thing in your paper here.
Yeah. So as I mentioned, you cannot randomize everything. So you just
Mm.
need to generalize.
Yeah, just scroll down a little bit. Like you have this thing that it's about sim to real lessons. Sys ID matters, correct URDF matters, don't write bugs. No need to do teacher student for sim to real. I think the last one is interesting. But anyway, like yeah, comment a little bit.
So yeah, first you need to system identification. You can just the randomization. You need to identify what's motor dynamics. So this is the thing that helped the most in our humanoid material. And also you need to get the correct URDF. So this is actually very hard even for companies like Unity or a lot of other companies. I mean, like if you can really get a correct URDF with correct mass and correct inertia, that's better than most of the companies.
Interesting. So you're saying that oftentimes the URDF, the starting may be wrong, and then you basically have to find out through
Yeah.
experiments.
So because like for simulator, there are actually I think there are two things to care about. One is about contact, so it is related to the simulation and your mesh. And another thing is about inertial, which means that if you just ignore the battery's mass in your base, then you can cut something to gap. And many companies just forget to add the battery mass. And also like then the third thing is about actuation. So like your motor in simulation is ideal, but in the real world, it's not ideal. So we use something like animal. We use the actual network, but maybe you can also use system identification. And on humanoid, we use the system identification to get a DC motor model so that we know that how unideal, so how far it is from ideal actuation, we can know that. So we simulate this thing in simulation, then it's more able to capture like the very nuances into gaps. And the first thing is about perception, but I guess it's not a big concern right now. Yeah, because like you have many ways to do perception, but different ways have different gaps. So there's no very principled way I'd say. And sometimes you can just overfit their task scenarios. So I'd say the most important things are inertial, contact, and actuation.
And how about
And
this no need to do a teacher-student thing for sim2real?
yeah, so like in the history, we do teach student because we want something like when we do not have perception, we do like reactive, robust control. So we can still see a lot of such works today. So they just do blind locomotion, but it's very robust because usually they train teacher policy that is privileged and they train student policy. Actually, like the point here is that you cannot easily directly train a blind student to do this kind of things. So the training is hard with pure MDP, but ideally you know that if you want a good performance on the pure MDP, you better just train it with PMDP. And also that teacher students are not always so ideal because you know there's something called teacher student gaps because teacher has more information. Information cannot be easily recovered for the students. There's always a gap for the student to replicate the teacher's performance. So if there is a big gap between MDP and PMDP, teacher student will be suboptimal, and it's usually over optimistic because the student might think is as capable as the teacher. So it will do some risky behaviors. And also, if the gap is small between MTP and PMBP, then you can directly train the student without the teacher. Yeah. So I think that the very limited cases are that you need a pure MDP, but you cannot directly train it. In this case, you need to teach a student.
Yeah. Well, thanks for the two thread. I wish more researchers, besides summarizing what they talk about the paper, also have one or two hot takes like the one you did. I think that was really cool. Yeah, I guess maybe just wrapping up here. Is there any limitations or future work that you hope to do as a
So one work is close to be finished. It's about doing parkour with this attention-based things because like previous parkour works are just assuming we have a big box, all our obstacles are like boxes, and we just climb a box-shaped things. Here, about the generalization, I want the same agile generalist to go count all kinds of trains. The first thing, so it's already almost finished. I'm just doing things.
Also with the humanoid.
Yes.
Also with humanoid.
Nice.
Okay, but for that you will need to upper body, right? Supposed to do proper parkour.
Actually, we have two lines. One is with upper body, one is without upper body. Both will have some new results.
Okay.
Man, I can't wait to see the demo for that one.
Yeah.
Cool.
The second thing is that I want to see the real 3D representation. It's still not clear how to do it, but I will explore it later.
That seems like a big one. That would be very interesting to see what you come up with.
And also I'm working on highlight autonomy because now that we already have these good controls, we need to be able to use them. So for example, for navigation in classical navigation, it's just about collision avoidance. You find a flat terrain and you go over the flat terrain, but now we can climb more complex terrains. We need a better planner for this kind of controllers.
All right, cool. Yeah, maybe a last question that we like to ask. Any interesting paper that you came across that you want to give a shout out to that really impressed you?
Well, actually, not sure if you have visited these papers, but you mean one paper or many papers?
What was the most interesting thing you saw recently, I guess?
Yeah, so about some recent works, there's another paper on science robotics. It's called RoboBody. I'm not sure if you have read that.
No. Which lab is it? RoboBody.
It's the cover paper from UCL and DeepMind. It's about you have multiple robotic arms and you use I/O to make these multiple arms to move in very constrained space.
Ballet.
Ballet. Okay, got it. Okay, cool. Now then, this is okay. I completely missed this one. I see it now.
Yeah.
Got it. Interesting.
I think this is the most recent work that really impressed me a lot. Yeah.
Oh wait, I think I saw this. I just didn't realize it was called RoboPapers. Okay, cool. All right, cool. Hopefully we can get them on the pod. Okay, sounds good.
Yeah.
I mean, thank you so much, Chong, for the time.
Thank you.
I thought, it was a very impressive work. I think he has a lot of implication, even just for teleoperation. Especially for, I think a lot of things maybe, for quite a while, I think maybe you still want a human to be so-called controlling, but very, very, maybe just turn left, turn right.
We want more higher level control. We don't want such low level.
It's not less human.
Yeah.
I want that I just point to something, then robot just do it.
Just go there. Okay, that's true.
Human may be for the humans doing less and less. Yeah, that makes sense.
Yeah, less and less. Okay, that's true. That's true. No, that's true. I mean, I think that there are, nearly all, practical use cases you want a human to just give even higher and higher level instructions. But then there's the other type, which is some people drive because they like driving. Even though they can take an Uber, right? So there is some joy sometimes for people to control hardware, robotic stuff.
Yeah.
So you guys know I do all this robotic game, robotic fighting thing. I think people do actually enjoy, just being in the control, but obviously it needs to still go through a decent teleoperating stack. And a lot of it, you still have to use something like what you built here. to make
Yeah.
the experience feel fun, and then so you take away some of the details and then let the humans have their fun.
Yeah.
So I think that's actually still another use case. Could be any, I don't know, like
Yeah.
consumer entertainment kind of
Yes.
thing.
Yeah.
Yeah. I mean, funny, like the
yeah.
generalization and perception kind of locomotion is very, very interesting, very compelling, really cool stuff. I think like that's one of those things where you can really see it. Like with a lot of the dancing robots, I think it's kind of hard to imagine them doing anything, right? Because it's always on a flat ground. Maybe I shouldn't say that in the recorded part of the podcast.
Yeah.
But like, yeah, it's like because like the real world is messy. There's lots of stuff around. It's very cool.
Yeah.
Exactly.
And
Anyway.
one specific I was also wondering about is like sometimes it's no some places like a gap you cannot step on. It's like you have a toy on the ground that you should not step on. Then it's more like a 3D.
Or you have a baby on the ground, you know,
Right.
you know, like a puppy, you know, like a kitten. You do not want to step on
exactly.
that. It's like a matter of life and death, yeah, at that point.
That task could be more challenging and also more worth studying. Yeah.
It's like actually, it seems like it's a fundamental part of getting a locomotion controller that you could deploy at home or in a real environment.
It's
Right?
true. Yeah.
So
Yeah, basically get self-balancing regardless of embodiment, but in a way that is very, environment aware, and then you react accordingly while trying to still get to the final goal that the human or some higher level planner is telling you to do. I think that is a real thing.
Yeah.
So, but yeah, very impressive, and I think cool. Well, yeah. Thank you so much, Chong. I think we need to get you on the pod ASAP once you have the parkour paper out.
yeah, look forward to the parkour stuff.
Yeah. All right, Chris, what have you learned today?
So I really like this paper. I think that there's a lot of interesting stuff here. I think it's some of the coolest locomotion results that I've seen. I think this might be true for you too, but it's like I love the focus on generalization, the real world demonstrations of the robots just going over clutter. It's all end-to-end RL, but with a clever architecture. The generalized is better. There's a lot of cool stuff to learn to like about it. What about you? What do you think?
Yeah, I mean, very impressive work. I wish he posts more of that video because it's hard to actually find the video, and it does. I don't think
he's
he's
super cool if you can
a,
find him. Yeah, that's
doesn't have the it doesn't have a website yet. I think super cool work. I thought it's I mean I think straight away I can think of like it's a way better teleoperation experience already. But I mean eventually whether it's teleoperated or not or just done by AI ultimately or fully autonomous, like basically you need very, very robust like environment aware kind of controller. I think his pipeline is very scalable. So yeah, it sounds like he's an even crazier one lining up, soon. So
yeah,
that would be cool. Yeah. I just hope he open source everything so that the community can build on top of it. Yeah. But I didn't even see this paper until you pointed out. So quick call. Yeah, I'm glad we got him in.
Yeah, thanks.
Yeah. So yeah, I guess until the next one. All right.
See you.
See ya, man.